Days of solid and liquid. So this is day one, and next day will be the final class of this chapter. So we are going to revise some important concept of it, and also we attempt some problem on JEE Main, PYQs, and NEET. Okay, so let's just get started with it. So the what are is elastic behavior of solids, and then stress and strain, Hooke's law, modulus of elasticity, in which we have three types of elasticity. Okay, three types of modulus of elasticity. Then we are going to see some properties of or some key points from this stress and strain curve. Then we will discuss the formula for elastic potential energy. And also we are going to do some PYQs also based on these topics. Then we are going to learn about pressure due to a fluid column, Pascal's law and its application, and effect of gravity on fluid pressure. So this is it we are going to revise today. So let's just get started with it. So firstly, if I talk about elastic behavior is that property of any substance or any material to regain its shape, to regain its shape after removal of applied force. Okay, so whenever we have a rod or if we have any kind of material, suppose this is the rod we have taken of length L, and we are going to stretch it. Stretching is only possible when we direction. Okay, so in this, what will happen? Due to these forces, the atoms inside this material also attracting each other. So the force present in between these molecules are called intermolecular forces or interatomic forces. Intermolecular force. So this intermolecular force is of attractive in nature. Okay, this is attractive in nature. If it is attractive, so if I talk about a single molecule, let's say these are two molecules and they are combined with each other with the help of these intermolecular forces. But when we applied the external force, okay, so these force try to reduce the amount of intermolecular force they are possessing. Okay, they are applied on each other. So due to these molecular forces becomes weak. Okay, weaker and weaker. So the separation between these molecules will increase. Hence, we will see a extension in length of the rod. Let's say this extension is of delta L. The initial length is L, and now it is extended by amount of delta L. Now, the force, external force we have applied continuous. But now if we remove this externally applied force, what will happen? This force has been removed. So if the force has been removed, only molecular forces came into interaction again, and they will attract the molecule to the same position, and hence the length will reduce to the original length. So this property of any solid is termed as the elastic behavior of solid, which means that after removal solid regaining its shape, we can say that that particular solid is elastic in nature. Okay, so this elastic behavior is because of interatomic slash intermolecular forces. Okay, got it? So this is it for elastic behavior. Okay, now what is stress and strain? So simple definition wise, what is stress? When you applied the external force to any particular shape, we have considered a rod of length L, and we have applied a force F perpendicular to the cross section. Okay, got it? So these stresses is defined as force per unit area. Now, there are three types of stress we have. And stress is nothing but when we apply the force, when we want to disturb the dimension of any particular solid. So the molecules inside that, the atom inside that will apply a force and resist this change in dimension. In respect to that, they developed a internal resistance force. Internal resistance force. So this internal resistance force per unit area is termed as stress. This is called the stress. Okay, got it? We have three types of stress: longitudinal stress, longitudinal stress. Another we have shear stress, and then we have bulk stress or volumetric stress. Okay, so we know that stress is resisted. Okay, we have applied a force on the both of the end, so molecule did not want to extend, so they resist that extension or that compression, and they will apply a resistance force from the inside, and that internally applied resistance force per unit area, you can say, is called as stress. So that area is also matter. If this is a cube, let's say this is a cube, and we are applied the force on these opposite ends to it. So this force is applied to the perpendicular to this area of cross section. So that particular stress is termed as longitudinal stress. It is termed as longitudinal stress, in which force divided by area, and force you have to take perpendicular. Okay, but what if I apply the force parallel to this face, parallelly, and this face is, let's say, fixed? So what will happen? This block will tilt somehow like this from the original shape. Let's say this angle is theta. Okay, so it is because of we have applied the force in parallel direction. So that stress is termed as shear stress when you apply the force in parallel direction per unit area on which you have applied that force. Got it? What if I have a sphere, stresses in each and every direction, there is a force is acting on that uniformly, and let's say the initial volume is V. So what will happen to this? The volume will decrease due to these forces, and you cannot say that this is acting on a particular cross section, because they are acting, this is a sphere, so they are acting in a volumetric sphere. Okay, so these types of stress is termed as volumetric stress, and this is nothing but pressure divided by area. Okay, volumetric stress is that pressure we have applied divided by per unit volume. Okay, got it? Now, give me a second. Sorry for the pause. So we are saying that bulk stress and volumetric stress. So this stress you can say is the change in pressure. Okay, because these forces, let's say F, are acting on this surface perpendicularly. So this is the property of stress. Got it? When force acting perpendicular to any surface in radial direction, so that you can consider is a pressure. So this will be a change in pressure. Got it? Now, modulus of elasticity. Before that, okay. So modulus of elasticity से पहले we will study about Hooke's law. Hooke's law. Now, what is Hooke's law? Hooke's law says that we know that key material can extend its shape or compress it up to a certain limit. Okay, when we extend, apply a force in equal and opposite direction, so that material can have an extension. But when we remove these forces, the property of elasticity says that it can regain its shape again. Okay, so Hooke's has connected the dots and relate that change in length or change in any dimension to the stress applied. Okay. Now, Hooke's law says that within within the elastic limit, within the elastic limit, stress is directly proportional to strain. Now, what is this strain? So, strain is nothing but strain is the ratio of change in dimension to the original dimension. Okay. These are also three types, because three types of stress we have. So based on that, three types of strain we have. Longitudinal stress, strain, shear strain, and bulk strain. Or you can say volumetric. In longitudinal strain, the stress is acting perpendicular to the length. So in this, there will be a possibility of change in length. So it will be given by change in length divided by original length. In shear stress, when we apply the force, it has a tendency to deform its shape by an angle theta. So we can say that if this shift is x, this length, side length of this cube is L. So we can say that shear stress is tan theta equals to x by h. Or this theta is very small, so we can say that theta is equals to x upon h. Now, bulk strain or volumetric strain, we know that when a force is acting uniformly on a sphere, that will reduces its volume. Okay, so we can say that it is change in volume divided by volume, original volume. Okay, so Hooke's law says that within the elastic limit, stress is directly proportional to strain. Okay, now to remove this proportionality sign, I will change the color here. Stress is directly proportional to strain. Now to remove this proportionality sign, we have to consider a constant. So that constant is nothing but stress is equals to modulus of elasticity multiplied by strain. Okay, so this is the Hooke's law. Okay, now based on the Hooke's law, we have three types of modulus of elasticity. Modulus of elasticity. Three types of modulus of elasticity. First is Young's modulus of elasticity. Which is given by longitudinal stress to the ratio of longitudinal strain. So it is given by capital Y is equals to F upon A divided by change in length over original length. Then we have a shear modulus of elasticity, or you can say that modulus of rigidity. It is also termed as modulus of rigidity. Modulus of rigidity. Modulus of rigidity is given by G, which is equals to shear stress, which is force parallel per unit area divided by shear strain, which is theta. Okay. And then finally we have bulk modulus of elasticity. Bulk modulus of elasticity is very easy. It is given by B is equals to bulk stress, which is change in pressure delta P divided by bulk strain, which is change in volume divided by original volume. Now, when we are changing the volume, we are decreasing the volume from initial to final. Okay, so in that case, this change in volume will be negative, but bulk modulus is a positive quantity. So we have to apply a minus sign here. Always remember that. Okay. Now, if I talk about the stress and strain curve, so we on the first axis we have taken stress, and on the second axis we have taken strain. We have considered a particular material, okay, and we are applying a force, let's say this is a road, and because of this stress, there will be a development of strain. Okay, so this force is gradually increasing. So if this force is gradually increasing, the stress will be gradually increased, or maybe the possibility that it can be increased. And in the similar way, strain also increases. So we will note that value and plot a curve which is called as stress and strain curve. Now, if we plot it for a ferrous material, okay, non-ferrous material. So these types of curve we have obtained. Now we have different points here. We have to understand what is these points convey to us. So if I talk about this point A, so before point A, you can consider this line. You can consider this line to be nearly a straight line. So that is why this this line you can consider it a straight line. So from here you can easily say that stress is linearly proportional to strain, and which is conveyed by us with the help of Hooke's law. So Hooke's law says that in the region of elastic limit, the stress is directly proportional to strain. And here we can see that this curve up to point A is following the Hooke's law. So this region under this curve is termed as the elastic region. Means up to this point, if you applied the force and remove it, then the material will regain its shape again. Okay. And that point is termed as proportional limit. Sometimes it is written as elastic limit and proportionality limit. But most of the cases, these points are very close to each other. So we can consider it by only one. Proportional imposed with the elastic limit. So up to proportional limit, or you can say elastic limit, the Hooke's law is valid. Okay. After that, on increasing the value of stress, the strain is increasing. Okay. But if you remove the stress in this region, the material will not gain it. Material will gain its shape, but Hooke's law is not valid. Which means you can also see this. There is a slight curve in from A to B, which means the stress is not directly proportional to or linearly vary with strain. Although if you increase the value of stress, strain is increasing, but not in a linear manner. So we can say that Hooke's law is valid only up to point A, but elastic behavior will be kept up to point B. So this reason you can say is the elastic reason. Got it? But the only difference is up to point A, Hooke's law is also valid, but from A to point B, only elastic behavior is there, but no Hooke's law and you can apply it. Okay. After point B, this point is called as the elastic limit or yield point. Okay. After that, if you will move, there is a sudden decrease in the, there is a slight decrease in the stress, but strain is increasing. And it is because of now at this point of time, the molecule have separated so far. So the so instead of applying a very large amount of stress, they will show you a kind of elongative behavior with a very small value of stress applied, because at that time the molecular forces are very weak in that molecule. Got it? So this point B is called the yield point, or you can say the upper yield point, and C is the lower yield point. Up to B to C, with the decrease in stress, there will be an increase in strain. Okay. Now, from point C to point D, this point D is the maximum value of stress that particular material can vary, and this stress is termed as breaking stress, or sometime it is called as ultimate stress. ultimate stress, which means it is the maximum stress that a material can bear. After that, when we achieve the ultimate stress, there is a down in stress, and this point E is termed as the fracture point. Got it? Now, this region is termed as the plastic region. Now, what is plasticity? When you apply the force, disturb the dimension of any particular body, and it is not, after removal of that force, the body is not capable of achieving or regaining its original shape. That behavior or that property of a material is termed as plasticity. Okay, so from point B to E, if you remove the stress at any particular point between B to D, there will be a permanent stress developed in the material, which means it cannot regain its shape originally as it was original. Okay, so let's say if a material is 10 centimeter low and you have applied a stress up to point D, so the 10 centimeters shape again, it will be like say 12 centimeter or 10.2 centimeter. So there will be a permanent stress, permanent strain developed in the material. So these points are very important. You can say from elastic limit or upper yield point to fracture point, the region is called as plastic region. And from point origin to point B, which is the elastic limit, the region is termed as elastic region. Hooke's law is only valid up to point A, because here the stress is directly proportional to strain. Got it? Now, so this is for this stress and strain curve. Now, elastic potential energy. So what is happening? Elastic potential energy is given by, let's say, delta U is equals to 1 by 2 times stress into strain into volume. And if you keep this value of volume in the left hand side, so you will have delta U upon per unit volume, which is termed as energy density. Energy density, which is equals to 1 by 2 times stress into strain. Okay, so what will happen when we apply the force in a particular material and when we stretch it, let's say, so the distance between these molecules will increase. So we know that at the distance between or the arrangement is disturbed, so this elastic potential energy come into contrast when there is a arrangement or disarrangement. So initially they are arranged, let's say this position, but when we apply the force and stretch it, so they have arranged themselves in a different position. So due to this extension, there will be a elastic potential energy stored in that system, and which is given by half stress into strain into volume. If you are able to calculate, if you want to calculate it per unit volume, this will be applicable for all the types of stress. It is applicable of on all the types of stress. Stress and strain. Okay, got it? So this is it for elastic potential energy. Now I want to discuss a very important formula for you with you guys, which is given by, mostly you will see a question of extension in length. So extension in length, extension in length, or you can say the change in length, is given by, let's say it is delta L. Delta is given by force applied multiply with the original length divided by the Young's modulus of elasticity multiply with the original area. Now in this expression, if force is varying with distance, so you can consider if force is varying with length, so you need to consider a very small change in length, which is, let's say, dl is equals to f into, for a very original length, of dx divided by y into a. And when you integrate it, you will get to know the total extension in length. Okay. Now, this formula you can also modify. If you apply the Hooke's law here, so energy you will give as 1 by 2 times stress, and we are considering the Hooke's law, which is given by stress is directly proportional to strain. And if I talk about the longitudinal stress, so it will be longitudinal stress is given by sigma is equals to Young's modulus of elasticity into epsilon, which is strain. So if you put the value of stress in terms of strain, so it will become 1 by 2 times y into strain ka square, epsilon square. This you can also apply. Okay. Now, similar way, you can put the value of strain. This is for energy density. Okay, so similar value, if you put the value of strain here, so you will get the expression in terms of stress. Now, look at this question. This is a previous year asked question. An aluminum rod with Young's modulus y is equals to 7.0 into 10 raised to the power 10 Newton per meter square undergoes an elastic strain of 0.04%. The energy per unit volume stored in the rod is, look, the concept that we have learned has been asked in the question. We know that energy density is given by 1 by 2 times stress and strain. Now here Young's modulus is given, which means stress we have taken as a longitudinal stress. So sigma is equals to y into epsilon, which is the longitudinal strain. Okay. So y is given you. If you put the value 1 by 2 times, stress will be y into epsilon and strain will be epsilon. So it will become 1 by 2 times y into epsilon square. Now we need to calculate the epsilon. So elastic strain is given to you as 0.04%. It is given in percent, so we need to convert it into, obviously, we need to convert it into a numerical value, which is 0.04 divided by 100. So you can say that it is 0.04 10 raised to the power minus 2. This is a unitless quantity because change in length divided by length. Same dimension is dividing the same dimension. So there will be no dimension of this. It is a dimensionless quantity. So u here will be 1 by 2 times 7 into 10 raised to the power 10 multiply epsilon square, which is 0.04, 0.04, 10 raised to the power minus 4. Now 2 will cancel out this time, 0.02. Okay. And this will become 10 raised to the power minus 2, 10 raised to the power minus 2, minus 4 we have. So it will become 10 raised to the power minus 6 finally. and we cancel it out with this. So U here is equals to 7 into 10 raised to the power 10 multiply with 2 into 4 10 raised to the power minus 8. Okay. Now 2 4 ja 8 and 8 5 ja 8 7 ja 56. So 5600 because this will cancel out 2 power of it. So this will become 5600 joule per meter cube. This is the answer. How simple is this? Okay. Now pressure due to a fluid column. Now what is a pressure? So firstly we need to understand the concept of pressure. Let's say here we have a surface, let's say, and this on this surface we have applied a force at an angle theta. Okay. Now you can resolve this component of these forces in two components, which is firstly is second is perpendicular to the surface. Now if you want to push this surface down, so which force is capable of doing that? This force, this perpendicular force is termed as thrust. Okay, got it? Now pressure is equals to thrust force, or simply the thrust force divided by area per unit area perpendicular to it. So this force is perpendicular to this area. So we will take pressure as thrust force per unit area, because itself force is not sufficient to give you a data. We need to consider the area also on which this force has been applied to see the impact of force. Okay. So the pressure is defined as thrust force per unit area. Got it? Now, this area is this surface. Let's say this area or this surface is perpendicular to the thrust force. Suppose we have taken this cross section. Okay. And we have applied a force in this direction. So if you want to calculate the pressure because of this force, so what area you should consider? No. If on this surface you are interested, so this force is perpendicular to this surface. So you can consider this. Okay. Now, if you resolve this area in two components, the first will be this. Let's say at angle theta. Or if I just change the scenario here, you will have the cross section like this, and a force is acting on this cross section in this direction. So you need to convert this area into perpendicular area, and that then the pressure will be force per unit area perpendicular. Okay, because on that particular cross section particular direction, and that will develop the pressure inside it. Got it? Now, due to a fluid column, so let's say we have considered a fluid column here, which is filled with fluid. Now, we want to consider, and we just invert it. We just invert it. And this is the cap here we have applied, and this is, let's say, water or any liquid. So this weight of this liquid is acting in downward direction, and this is the area. Now this force is acting perpendicular to this area. So we can say that this is the pressure development here, which is given by mg divided by area. Okay. Now if this is a fluid, so you can write the mass of fluid is given by density of the fluid multiplied by the volume. So you can say that it is rho v G. Okay, per unit area. Got it? This is the pressure. Now, got it? Okay. So this is it for the pressure. We will discuss it more in the upcoming slide. Now, effect of gravity on a fluid pressure. So what will happen? We have considered this bucket filled of fluid, and we have considered this imaginary cylinder we have considered here. Fluid cylinder, your fluid element you can say. This point is 1, this point is 2, and we have a height of h. So we can say that the pressure is acting on this surface, try to push this surface down. All in uniformly. So this is pressure, let's say P1, and here the pressure will act in upward direction. So here pressure will be P2. Now, when reaching from P1 to P2, we have the mass of the cylinder also, which is filled inside the cylinder, which is acting downward direction. Let me change the color. This mass of the fluid is acting in downward direction, which is mg. So we can say that this fluid is static. So for static fluid, this will be in equilibrium. If it is in equilibrium, there is no net force acting on the cylinder. So sum of all the forces will be 0. So we can say that P1 plus mg minus P2, because P2 is in the opposite direction. So P1 minus P2, you can say that it is m into g. But one of the mistake that we are making here is we are considering the pressure, but we are applying the force. Mg is the force. So P1, due to this P1, force will be F into F1 into area. P2 will be F2 into area. So F1 is given by P1 upon A, and F2 is given by P2 upon A. Okay. So we can say that F1 minus F2 is equals to mg. Okay. If you put the value here with the terms of pressure, P1 upon A minus F2 upon A, sorry, P2 upon A was to mg. So it will become P1 minus P2 was to MA area into G. Now, this mass you can term in terms of volume also. So this mass is given by density per unit volume. Sorry. Density of the fluid is given by rho, mass upon volume. So mass is given by pressure is force upon area. This is force upon area. So F1 will be P1 into A, and this will be P2 into. So this will multiply, and so that it will come into the denominator. We have taken area as common. Okay. Now mass is given by density into volume. Volume you can write here as height of this cylinder multiply with the area. So it will be area into height. Now similar way में we can put the volume here, mass into volume. P1 minus P2 is given by mass, area, height into gravity divided by area. So P1 minus P2 here is rho g. So this is the pressure difference, which means if we are going in depth, the pressure will increase. Okay. Put it. Now, So this you can apply here. Okay. Now, if I consider few cases here, pressure for pressure in accelerated vessel. So if a vessel here is going up with an acceleration is given by now initially if this is no acceleration we can write it rho g h if this is h, but now there is an acceleration in upward direction, so there will be an effective acceleration which is given by g plus a into h if it is moving up. If it is moving down, rho g minus a for moving down. Now if it is moving in horizontal direction with an acceleration a, so there will be a slight change in the surface, and let's say this height is h1 and this height is h2, and this shape changes with an angle theta. This is the final surface we have. So we can say that h1 minus h2 by length of this vessel is L. L is given by tan theta, which is given by A by G. This is another formula. Or you can say that change in pressure in horizontal level now. Let's say this point is 1, this point is 2. So P2 minus P or P1 minus P2 will be given by minus rho length of the vessel into acceleration. So it can be P2 minus P1 equals to rho into L into A. So if the vessel is accelerated horizontally, you can write it. The pressure will be drop in the horizontal level also. Okay. In general case, if this is the vessel and moving at this particular angle with an acceleration A, so in vertical direction, you can write the acceleration will be, if you resolve it into two components, this will be ax, this will be ay. So accordingly, you can write the change with in upward direction, the effective acceleration will be g plus ay, and in horizontal direction, it will be rho l ax. Okay. Now, Pascal's law in application. Pascal's law is very simple. It states that in a static fluid, pressure will be same for all the points at same level. Okay. And any change in pressure will be equally transmitted to the entire fluid without any loss. So without any loss, any change of pressure will be equally transmitted to the entire fluid, and that fluid must be incompressible. Incompressible. Okay. Application of Pascal's law is, if you see, this is the let's say jar we have, and if you consider this is 0.1, this is 0.2, this is 0.3, but they are at the same height, or you can say the same depth. So the pressure P1 is equals to P2 is equals to P3. Okay. Application of this will be hydraulic lift. Hydraulic lift, hydraulic brakes. Okay. So these are the application of Pascal's law. Now, this is the question based on the Pascal's law. So a hydraulic automobile lift is designed to lift a vehicle of mass 5000 kg. Let's say this is the hydraulic lift. Hydraulic lift में we have two limbs, and between these limbs the incompressible fluid is filled, and we have arranged it with the help of piston. So on the smaller side we apply the force, and in the bigger size we put the vehicle or anything that we want to lift up. So this lift is designed so that it can lift a vehicle of mass 5000 kg, which means the weight of the vehicle is 5000 into g, which is 50,000 Newton weight it can lift. The area of cross section of the cylinder carrying the load is 250 centimeter square. This, which is carrying the load, has an area A2, let's say 250 centimeter square. The maximum pressure of the smaller piston would have to bear is, so what is the pressure to be bear by this smaller piston? So we know that the pressure is same, and the change in pressure is also equally transmitted to this. So the pressure at this surface will be P2 is equals to F2 divided by area. Now how much force it can lift? How much force is applied here? The same that it can lift maximally. So maximum weight it can lift is 50,000 Newton. So it will be 50 by area. You will have to, this will cancel out this. So it will become 200 into 10 raised to the power 4 Newton per meter square, which is the pressure. Now, according to Pascal's law, according to Pascal's law, the same pressure is here. P1 will be is equals to P2, because same pressure will be transferred. The difference of pressure will be transferred to this end. Okay, so you can say that P1 is equals to P2. So P1 2 power 10 raised to the power 6 Newton per meter square, and we know that 1 Newton per meter square is equals to Pascal. The power 6 Pascal. So this is it. So this is it from my side. Thank you so much for your time. I hope you enjoy this session. So we will meet in the next session with more questions and the remaining part of this chapter. Okay. So take care of yourself. Involve yourself in studying. Thank you so much.